Okay, in case of 5404, CHO5404, in asymmetric synthesis, the important remaining part is now stereoselective aldol reactions, predicting relative stereochemistry through transition state. Okay, so what type of transition states involved in that aldol reaction we will see now. Model Zimmer-Traxler. Okay, so what is Zimmer-Traxler we will see, and some specific reactions like Evans aldol, Mukayama, and Mosami reaction. We will finish in this lecture. So let's go for the aldol reaction, which we can say now we are going to see the stereoselective aldol reaction. That means we are going to induce chirality into the beta hydroxyketone, and we have to give, or we have to identify, okay, which diastereoisomer is going to form as a major compound, which one is going to form as a minor compound. Okay, so normal we will go through first basic aldol reactions now. So here is the general reactivity. Normally we do take aldehyde or ketone, and this is base catalyzed. This aldol reaction is base, either base catalyzed or acid catalyzed. So here we have taken the ketone, base or acid catalyzed, and we are going to react this ketone with another second molecule of aldehyde, okay, to get beta hydroxy ketone. Okay, so this is our main product. So reaction can be effected under acidic or basic conditions. Here I have given the mechanism for when acidic catalyzed, what will be the same, and when under the reaction is base catalyzed, what will be the same. So we'll go through a little bit through the mechanism. So ketone, again here ketone. Okay, ketone, you have requirement for the aldol condition. That means you should have active methylene groups. Okay, so active methylene group is nothing but the, you should have at least one hydrogen next to the carbonyl group, acidic hydrogen next to the carbonyl group. That means we should have requirement is that you have acidic hydrogen in your molecule. Okay. So on treatment with H plus, you are getting protonation at oxygen atom. So this protonation makes the carbonyl carbon more electropositive to attack by the to generate this enolate now. So here we are going to generate enolate. So here we have generated enolate. Okay, so we are going to react this enolate with second molecule of ketone. Okay, second molecule of ketone here we have taken, and by reaction of this in between this nucleophilic enolate and this ketone, another next molecule of ketone or aldehyde, anything, we do get beta hydroxy ketone as a aldol product. Okay, so this is acid catalyzed reaction. What is base catalyzed reaction? As this requirement is we should have at least one acidic hydrogen atom. So this acidic hydrogen atom getting abstracted by the base anyways, any OH also you can use. There is generation of enolate. Okay, negatively charged oxonium ion. Okay, carbon carbon double bond is here. This enolate ion, nucleophilic enolate ion, is going to react with another molecule of the aldehyde to give this type of uh, our beta hydroxy ketone. Okay, so this is these are the acid and base catalyzed reaction, and we'll go through the some different reactions. Self condensation. To most of aldehydes we can react in place of NaOH to give beta hydroxyketone. Intramolecular um, aldol reaction to get this cyclic product. Then again, 2 moles of ketone we can react with each other to get the beta hydroxyketone. 2 moles of base catalyze. 2 moles of ketone acid catalyzed reaction. We do get this type of product. So this is some different equilibrium conditions. Now we will see mixed aldol reaction. So 1 mole of aldehyde and another some different types equilibrium. That means some unsymmetrical aldehyde we can take base catalyze. So beta hydroxyketone. So here is also one mixed aldol product you will get. Okay, self condensation. That means only this acetaldehyde will react. That one will give one product, and this acetaldehyde and this another aldehyde, they will react with each other, you will get another product. Okay, so two different types you will get, two different types of products you will get if you will take different molecules of aldehydes, two different molecules of aldehyde. Okay, so with black color showed things you can see in the product black colored bonds that moiety comes from the starting material, and red colored moiety comes from the starting material. This is the thing. So here also now this molecule it can also get condensed with each other. These two molecules they can react with each other, and that is the self condensation product. And then again this molecule it will react with this one to give this type of mixed aldol product. Okay, so very beautiful reaction. Then next one component is non-enolizable and one component is enolizable. Okay, this is also one variation in aldol reaction. So this is non-enolizable, this is enolizable. On potassium hydroxide base catalyzed reaction, we do get normally this product. Non-enolizable component, enolizable component, base catalyzed. This is the product. One component is more acidic than the other. So here, this one is highly acidic compared to this. So sodium hydroxide. So we can get this type of product. So many variations we can see in case of aldol reactions. Now one more things, mixed aldol. Again, the next thing we can aldehyde plus ketone we do normally call Claisen split condensation. So this type of product also we get kinetic conditions. Ketone we are going to react with lithium diisopropylamine minus 70 degrees centigrade, generation of enolate, and this enolate react with the second molecule of aldehyde. So we will get this type of product. So pay attention. So different things we can observe in this case in case of aldol reaction. Now what is the main thing to go for the stereochemistry of the aldol reaction? What is the stereoselective aldol reaction? So what how to go for the identification of this particular chiral carbon atom which is present in the product, how to identify them or how to identify the product formation, which one is syn, which one is trans. So normally it depends totally upon the enolate formation in the mechanism. For first thing, we have to pay attention, total attention on the enolate formation. Whether our enolate form those enolate form they are Z enolate. Z means cis. Okay, so pay attention. O minus and alkyl group they are present on the same side of the carbon-carbon double bond. So Z enolate. From Z, if we will start with the Z enolate, we will get the syn product. Okay, so formation of beta hydroxyketone. So we are going to create new chiral center where the hydroxyl group is present. Okay, this carbon is new now generated chiral carbon atom, and we should have identify the stereochemistry of this newly generated chiral carbon atom which possesses hydroxyl group and already present carbon atom. Okay, so that one we have to go for the stereochemistry of these two functional groups of chiral carbon atoms, whether they are cis syn to each other or whether they are anti to each other. Next criteria, if we generated Z enolate, okay, pay attention, Z enolate O minus and alkyl group R dash, they are opposite to each other. Okay, E enolate, sorry, E enolate, trans enolate on treatment with the aldehyde, that one will give anti product. Okay, so this is the main thing we will see in detail now. What is how this Z enolate gives syn and how the E enolate give anti product. Generalization, Z enolates thermodynamically product gives predominantly syn aldol product. E enolates kinetically favored give predominantly anti aldol product. Diastereoselectivity selectivity higher with Z enolates. So let's see what are the mechanism and what are the Zimmermann Traxler Zimmermann cycle transition state.